Good morning everyone. I am Suprabha an MSc Physics student at IIT Guwahati. Today I will discuss moment of inertia of a rod, a ring and axis theorem. First start moment of inertia of a rod. Let's consider this is the rod. Here the length of this rod is L and mass of this rod is M, and the rotational axis which is one end of this rod and it's perpendicular to its length. Therefore we draw the rod. This is the rod and L is the length of this rod and M is the mass of this rod. And this is the rotational axis. Here, this is the uniform rod, so their mass distribution of this rod is uniform. Therefore, linear mass density lambda equal to mass per unit length. Let's take the small element of this rod. This is the small element of this rod at distance x. And mass of this small element is delta m and length of this small element is delta x. Therefore, mass density of this small element is delta m by delta x. Therefore, delta m equal to lambda times x. Okay. Now I derive the moment of inertia of this small element. Therefore, moment of inertia Br of this small element is equal to mass times x, distance x square. Therefore, x square. Okay. But we need to obtain the moment of inertia of this rod. So we take integration at x equal to 0 to x equal to L. Okay. Therefore, I equal to 0 to L times. Now put the value of L. Here put the value L. Therefore, lambda times dx. Here lambda is the constant, so lambda take out of integration. Therefore, I equal to lambda times here lambda is mass per unit length. And for the integration condition, x triple m equal to x triple m plus 1 by m plus 1. Therefore, x square equal to x triple 3 by m plus 1 and 0 to m by l, l cube and therefore, m l square by 3 is the moment of inertia of this rod. Now I derive the moment of inertia of this rod while the axis of rotation is passing through the center of mass portion. This is the rod and the axis of rotation, let's consider this is the axis of rotation which is passing through the center of mass portion. And similar length of this rod is L and mass of this rod is M. Now draw. This is the rod while axis of rotation passing through this center of mass and A is the length of this rod. Therefore, this distance is L by 2 and this distance also is L by 2. As a similar case, we take the as the previous case we the small element. Therefore, this is the small element. Here its dx and mass is dm and distance is. Okay. Therefore, the mass density lambda equal to m by l and linear mass density in this small portion is delta m by 2. Here it's uniformly distributed mass, so therefore it's called the linear mass density. Therefore, moment of inertia of this small portion di equal to mass of this small element and distance. Now we need to find the moment of inertia of this rod while the axis of rotation is passing through the center of mass portion. Therefore, we take the integration at the limit. Here this portion is minus L by 2 and this portion is plus L by 2. At the limit minus rod limit is minus L by 2 to plus L by 2. Therefore, I equal to minus L by 2 to plus L by 2. Therefore, put the value di dm times x square minus L by 2 to plus L by 2. While dm is lambda times d. Therefore, lambda is the constant, so this is taken out of integration. Minus L by 2 to plus L by 2. Now integration limit x to the power n equal to x to the power n plus 1 by n plus 1. Therefore, lambda equal to minus therefore, lambda by 3, n by 2, q minus of minus L by 2. Here put the value of lambda, L by L times 3 and this is 2 times LQ by L square by we get the moment of inertia of this rod while the axis of rotation passing through this center of mass portion. Now I discuss the axis theorem. Now I start the parallel axis theorem. Parallel axis theorem while the axis of rotation is shifted from the center. Let us consider this is the axis of rotation, this is the center portion and this is the shifted axis of rotation. Therefore, this is the new moment of inertia about the new axis and this is the moment of inertia about the center of mass axis and this is the mass of this body and this is the distance between the center of mass axis and the new axis. Now I using the apply the parallel axis theorem of this rod. Let us take this is the rod and this is the moment of inertia along this center portion. And now take this axis is shifted from the center portion to end portion. Therefore, I equal to I. Now let's draw. Rod is this distance is the L by and M is the mass of this rod. Okay. Now we already calculated the moment of inertia along the center of mass portion. So we put this value m square by 12. Mass times distance. For distance here, this distance is L by 2. L by 2 square. Now outside the m square and for 12. Then we get m square. Okay. So we use the parallel axis theorem. We get the moment of inertia is m square by 2. It indicates that while the axis is shifted, the increase is moment of inertia because of this more masses.